These are the answers to homework 3C. Question number 1. For the reaction, 2H2S gas plus SO2 gas is in equilibrium with 3S solid rhombic plus 2H2O gas. A, calculate the delta G naught at 298 Kelvin. So for this reaction, to calculate the standard free energy change, we're going to use the standard free energy of formations found on handout 5, products minus reactants. So it's going to equal, starting on the product side, 3 moles multiplied by the standard free energy of formation of sulfur in the rhombic form, which is standard state, which is 0, plus 2 moles of gaseous water multiplied by its standard free energy of formation, which is negative 229 kilojoules per mole. To the reactant side, minus 2 moles of H2S multiplied by its standard free energy of formation, which is negative 34 kilojoules per mole, minus 1 mole of SO2 multiplied by its standard free energy of formation, which is negative 300 kilojoules per mole. The moles cancel out in each of the terms. Answer comes out negative 90 kilojoules. B, is the reaction spontaneous under standard conditions? The delta G naught, if it's negative, means the process is spontaneous under standard conditions. C, if the pressures of each of the gases are H2S, 1.0 times 10 to the minus 4th atmospheres, SO2, 1.0 times 10 to the minus 2nd atmospheres, and H2O, 3.0 times 10 to the minus 2nd atmospheres, calculate delta G at 298. So this is a non-standard state reaction. We're going to have to calculate the Q value. Then when we add RT natural log of Q to our delta G naught that we calculated in part A, we'll determine the non-standard free energy change for the reaction. The Q expression is products over reactants, and in terms of partial pressures, it's the partial pressure of H2O vapor squared divided by the partial pressures of H2S squared and SO2. The values given in the problem are here. When they're plugged in, the Q value for this particular instance is 9.0 times 10 to the 6th. To calculate the free energy change for the reaction now at 298, we'll use the standard free energy change, which was negative 90 kilojoules or negative 90,000 joules, plus R, 8.314 joules per Kelvin, multiplied by the temperature of Kelvin. Kelvins cancel out, so this term will be in joules, and it'll match the first term, which is in joules. And we have to multiply it by natural log of 9.0 times 10 to the 6th. If you calculate this out, this comes out negative 50,000 joules as the delta G for the reaction, or negative 50 kilojoules. D says, is the reaction spontaneous under the conditions in C? And because the answer came out negative, the answer is yes, it is spontaneous, although it's not as negative as under standard conditions, so it's not as spontaneous, but it is still spontaneous. Number 2, for the reaction, Cl2 gas plus I2 solid is in equilibrium with 2 ICl gas. Given the standard free energy of formation of ICl is negative 5.5 kilojoules per mole, answer the following questions. A, calculate the delta G naught at 298 for the reaction. So to calculate the delta G naught for this reaction at 298, it's just products minus reactants. And because ICl was not listed on handout 5, I actually gave it to you in the problem here. So we're going to go 2 moles multiplied by the standard free energy of formation of ICl, minus 1 mole multiplied by the standard free energy of formation of elemental chlorine, which is 0, and then minus 1 mole multiplied by the standard free energy of formation of 1 mole of I2, which is solid, which is 0. And this turns out to be negative 11.0 kilojoules. B, is the reaction spontaneous under standard conditions? The answer is yes, because the number came out as a negative value for your delta G naught. C, predict whether the equilibrium constant will be greater than 1 or less than 1 at 298. So the sign of the delta G naught predicts the magnitude of the equilibrium constant. And in this case, because the delta G naught value is a negative value, that means that the equilibrium constant is going to have to be greater than 1. D, calculate the equilibrium constant at 298. This is done with the relationship between the equilibrium constant and delta G naught, which in its original form was delta G naught equals negative RT, natural log of KEQ. But solving it for the KEQ, it's going to be E raised to the negative delta G naught over RT as a power. The value for the delta G naught will have to be switched to joules, so it's negative 11,000 joules, divided by R and T, the T being 298 Kelvin, and therefore the equilibrium constant for this reaction comes out to be 84.8, which, as we predicted in question C, is a value greater than 1. E, does the equilibrium constant favor reactants or products? What does this mean? Well, if the ratio of products to reactants is bigger than 1, you'll have more products at equilibrium. We say that favors products. If the equilibrium constant is less than 1, that means in the fraction, the denominator is bigger where the reactants are, so we would say it favors reactants. This equilibrium constant is greater than 1, so therefore we would say it favors the products. Number 3, for the combustion of liquid methanol, CH3OH plus 1.5 O2 is in equilibrium with CO2 plus 2H2O liquid. A, calculate the delta G naught for the reaction at 298. So using the data from handout 5, we're going to go standard free energy of formation of products minus reactants. So starting on the product side, 1 mole of CO2 multiplied by its standard free energy of formation, plus 2 moles of water multiplied by its standard free energy of formation. This is a liquid, not gas, thus negative 237 kilojoules per mole. To the reactant side, minus 1 mole of methanol multiplied by its standard free energy of formation, and then minus 1.5 moles multiplied by oxygen's standard free energy of formation, and this is an element in its standard state, so its value is 0. Moles all cancel out. This comes out negative 702 kilojoules as the standard free energy change for this reaction. B, is this spontaneous under standard conditions? Yes, because it's a negative number. C, predict whether the equilibrium constant will be greater than 1 or less than 1, and because this is a negative value for the delta G naught, that means that the equilibrium constant is going to have to be greater than 1. D, calculate the equilibrium constant for this reaction. So this is calculated from the delta G naught the same way we did it in the last problem. This time, when we switch the delta G naught value into joules, it's going to be e to the negative 702,000 joules divided by R times T, which actually turns out to be e to the 283. And if you try to do that in your calculator, if you have a fancy calculator, you're going to get the answer. But if you have a regular old standard calculator, it can't do that because the answer comes out to be bigger than 9.99999 times 10 to the 99th. And many calculators can't show an exponent of 10 to the 100th. So if this is on the test and you want to get this right, you're going to have to outsmart your calculator. If you recognize that e to the 283rd can be broken up into 2 factors, and what 2 factors might you use to multiply to make e to the 283rd? Because we're not getting the answer of 8.04 times 10 to the 122nd because your calculator is not being able to do that. Well, what you can do is if you multiply 2 things together to equal e to the 283rd, what happens to the exponents? They have to add up to make 283rd. So I could say that this would have to be e to the 183rd multiplied by e to the 100th. Now, each of those numbers can be calculated in your calculator, so you have to calculate each of those 2, and then you'll actually have to manually multiply those together. So the 2 numbers you would get in your calculator would look like this, 2.99 times 10 to the 79th, and the second factor that I've made up, 2.69 times 10 to the 43. So on your calculator, multiply 2.99 by 2.69, that's where I get 8.04, and then you add the exponents. 10 to the 79th times 10 to the 43rd is 10 to the 122nd, and that's one way to get around your calculator not being able to calculate such a large value. E, does the equilibrium constant favor reactants or products? Because it's greater than 1, that means it favors the products. F, what effect would an increase in temperature have on the spontaneity of this reaction? Good question. Couple of ways to think about this. If you know this is a combustion reaction, one thing you might have been able to do, so combustion reactions, why do we burn things? To give off heat. These are exothermic processes. If they're exothermic, that means in the reaction, according to Le Chatelier's principle, you could put the energy on the right side. And if you increase the temperature, you're increasing energy, that's going to make it shift to the left. That decreases the spontaneity of the forward reaction. So we didn't calculate it, but I just sort of common sense knew that a combustion reaction is exothermic, so delta H naught is negative. Higher temperature means the energy which you place on the right side would cause the equilibrium to shift to the left. And if it shifts to the left, that means the forward reaction is less spontaneous. Or if you use delta G naught equals delta H naught minus T delta S naught, In this reaction, the delta S value is a negative value because we're going from 1.5 gas molecules to only 1 gas molecule. We're decreasing the amount of gas. The entropy change is negative. So if you put a negative value in place of delta S naught and raise the temperature, you're making that second term bigger, and the negative of a negative makes that second term a positive. So you're going to be adding a bigger positive number to delta G, which means it's not going to be as negative. So a higher temperature means a more positive second term. And if that second term is more positive, delta G will come out to be more positive, which means less spontaneous. So either way is a way to answer that question. G, what effect would an increase in pressure have on the spontaneity of the reaction? When you increase the pressure, we know that Le Chatelier's principle, the reaction will shift to whichever side of the equation has the lesser number of gas molecules. So in this particular case, we have 1.5 gas molecules on the left, we have 1 gas molecule on the right. So there's less gas product molecules on the right side, so that means the equilibrium will shift to the right, and if it shifts to the right, that means the forward reaction would be more spontaneous. Or, if you think about this relationship here, if you have a reaction under standard conditions, which is what we're assuming here, that means that the Q value has to be pressures of 1 divided by pressures of 1. Q is going to wind up having to be 1. So what would be the Q value of the reaction here? It'd be the pressure of CO2 is 1, the pressure of O2 is 1, and 1 to the 2/3 power is just 1. So this is going to come out to, because Q is 0, just delta G equals delta G naught. If you increase the pressure, you do that by decreasing the volume. And if you make the volume smaller by, let's say, a factor of 2, you're going to double the pressures or double the molarities. So when we make this container smaller to raise the pressure, those pressure values in my parentheses are going to each double. If we double those now, 2 divided by 2 to the 3/2 power does not equal 1 anymore, and this log term turns out to be negative 0.35. So therefore, we're adding to our delta G naught value a negative term, and if we're adding a negative term to the delta G naught, we're making it a more negative number, so the reaction will be more spontaneous. Just another way to do that. Number 4, I've given the equation for acetic acid ionizing in water. At 298 Kelvin, the delta G naught of formation for acetic acid is negative 399 kilojoules per mole, and the delta G naught of formation for the hydrogen ion is 0. The delta G naught of formation for the acetate ion is negative 372 kilojoules per mole. Calculate the delta G naught for the reaction. Without using handout 5, I've given you all the necessary data, so we're just going to go products minus reactants. 1 mole of hydrogen ion multiplied by its standard free energy of formation, plus 1 mole of acetate multiplied by its standard free energy of formation, minus 1 mole of acetic acid multiplied by its standard free energy of formation. Answer comes out 27 kilojoules. B, is this spontaneous under standard conditions? The answer is no, because the delta G naught value came out to be a positive number. C, predict whether the Ka of acetic acid will be greater than 1 or less than 1. Because delta G naught is positive, that means the equilibrium constant has to be less than 1. D, from the standard free energy change of the reaction, calculate the Ka of acetic acid. So that's just an equilibrium constant. We calculate it by going e to the negative delta G naught over RT, just making sure we switch the delta G naught into joules instead of kilojoules. This comes out 1.8 times 10 to the minus 5th. C, what is the Ka value for acetic acid found on handout 3? If you look it up, 1.8 times 10 to the minus 5th. Are you amazed and stupefied by that? Pretty good correlation there. F, if the concentrations of each species are acetic acid 0.100 molar, hydrogen ions 1 times 10 to the minus 7th molar, acetate ions 1 times 10 to the minus 7th molar, calculate delta G for this reaction at 298. So now that we have non-standard condition, we need to calculate Q so we can add RT log of Q to the delta G naught that we calculated earlier. The Q expression is products over reactants, and if we plug the 3 molarities into the Q expression that we're given in the problem, we calculate a Q value of 1.00 times 10 to the minus 13th. So the delta G of this reaction now under these conditions will be our delta G naught value, 27,000 joules, plus RT multiplied by the natural log of 1.00 times 10 to the minus 13th, and that comes out negative 47,000 joules. Gee, is this reaction spontaneous under standard conditions? The answer is yes, because it's a negative number. So now, with these really low concentrations of the products, the forward reaction would be spontaneous for the system to reach equilibrium. 5. Metacresol, which will be represented by HCre, is a weak organic acid with a Ka of 1.0 times 10 to the minus 10th. A, write the equilibrium constant expression for the ionization of metacresol in water. So what would the reaction be? It would be the metacresol plus water donating a hydrogen ion to produce a hydronium ion and the Cre minus ion. The equilibrium constant expression for this is just products over reactants, hydronium times Cre minus molarities divided by the metacresol concentration. B, what is the concentration of the Cre minus ion in a 1.00 molar solution of metacresol in water? To calculate an equilibrium concentration, we need to use an ICE table to do this. So, flash from last test, we write our reaction that we know the equilibrium constant for, which is the ionization of metacresol. Initially, they say it's 1.00 molar. It's a weak acid, so some small amount of it ionizes, so that'll be X. So X molarity will react away. You'll form X molarity of hydroniums, X molarity of the Cre minus ion, and at equilibrium, we'll have 1.00 minus X molar of the metacresol and X and X of each of the products. If we want to solve this, we relate the equilibrium molarities to the equilibrium constant through the equilibrium constant expression in part A. So if we plug in the Ka value and the 3 equilibrium molarities, we can solve for X. And I'll do this by assuming X is so small, I'll ignore the X in the denominator. So it's just going to be 1.0 times 10 to the minus 10th equals X squared over 1. And that comes out pretty easily. X is 1.0 times 10 to the minus 5th molar. The question said, what is the concentration of the Cre minus ion in this solution? Well, under the equilibrium line under Cre minus, it says X. So X is the answer. That's the concentration of the Cre minus ion in this solution. C says, what is the pH of this solution? Well, pH comes from hydronium concentration, and at equilibrium, the hydronium concentration is X. And so if we just take the negative log of whatever X is, that's going to be the pH, and to 2 significant figures, comes out 5.00. D, predict whether delta G naught for the reaction will be greater than 0 or less than 0, in other words, positive or negative. And because our equilibrium constant is less than 1, that means that the delta G naught would have to be a positive value, greater than 0. E, what is the standard free energy change for the ionization of metacresol in water? So if we know the equilibrium constant, we can calculate delta G naught through this expression. So the R value, 8.314 joules per Kelvin, temperature 298 Kelvin, natural log of the Ka, and you take the negative of that, delta G comes out 57,000 joules, which was a positive number as we predicted. Question number 6, and now this one comes from what we did in experiment 15. The solubility of potassium chloride in water is 347 grams per liter at 20 degrees, 561 grams per liter at 60 degrees, and 802 grams per liter at 100 degrees Celsius. Calculate the KSP for potassium chloride at each temperature. So you're given solubilities. You can calculate a KSP if you know the molar solubility for the salt. And so we're going to have to convert the solubility in grams per liter into moles per liter. And then along with an ICE table, we can calculate what the KSP would be. The KSP is the equilibrium constant for a solid salt dissociating into ions. And initially, if we don't have any ions present, these would be 0 and 0. When X amount of the KCl dissolves, you'll form X molar of potassiums, X molar of chlorides, so those will be their equilibrium molarities. They're related to the equilibrium constant through the equilibrium constant expression. KSP equals potassium ion times chloride ion. And now that's going to equal X times X. So if we want to get the KSP, we have to know the value for X, and the secret here is X equals the molar solubility of the KCl. So if X is the molar solubility of KCl, all we have to do is switch the solubility from grams per liter into moles per liter by using KCl's molar mass. 74.55 grams on the bottom, mole on the top, and that'll give us the moles per liter as to how much KCl is dissolved, which is 4.655 molar. So that has to be the value for X. So the KSP is going to be 4.655 squared, which comes out a really big number. We're actually not used to that. But our tables for KSPs back on handout 4, those are for very insoluble salts. That's why their KSPs were 10 to the minus 5th, 10 to the minus 15th. They were really small numbers. KCl is very soluble in water, so you can actually dissolve a lot of it. So you see a very big KSP value, in this case 21.7. So that's the calculation at 20 degrees. The calculation at 60 degrees and 100 degrees are exactly the same, except you have to calculate the new molar solubilities because you dissolved 561 grams per liter of KCl at 60 degrees, and you could dissolve 802 grams per liter at 100 degrees. So I'm not going to do those calculations completely for you, but if you calculate the molar solubility of KCl at 60 degrees, it should have come out 7.525. So if that's the value for X, you square that, and you get the KSP at 60 degrees. And then if you calculate the molar solubility at 100 degrees, that came out 10.76 molar. So if that's the value for X, you square that, and the KSP at 100 degrees comes out 115.7. B says determine the heat of solution and the entropy change of the solution of potassium chloride by using a Van't Hoff plot, as we did in experiment 15. So from this equation here, relating delta G with delta H and delta S, if we divide the entire equation by negative T, or actually just by T at first, we'll get delta G naught over T equals delta H naught over T minus T delta S over T, and the T's cancel out the last term. So we essentially have delta G naught over T equals delta H times 1 over T, then minus delta S. And this fits the form Y equals mx plus b. So if we graph delta G naught over T versus 1 over T, we're going to get what's called a Van't Hoff plot. Now, we've got data at 3 different temperatures, 20 degrees, 60 degrees, and 100 degrees. I'll switch those to Kelvin, and I'll have my 1 over T values for X. To get my Y values, I need to calculate the delta G naughts, and we have the KSPs, which are the equilibrium constants. So you can calculate the delta G naughts from the equilibrium constants. And we do that this way. At the first temperature, delta G naught at temperature of 20 degrees Celsius will be negative R, multiplied by the temperature in Kelvin equivalent to 20 degrees Celsius, which is 293, and multiplied by the natural log of the equilibrium constant at 20 degrees, which was 21.7. So I get a delta G naught value at our first temperature of negative 7,493. At our second temperature, which is 60 degrees Celsius, we just use the Kelvin equivalent of 60 degrees and put in the equilibrium constant at that temperature. So the temperature is 333. The equilibrium constant was 56.63. So the delta G naught at this higher temperature becomes negative 11,175. At the third temperature of 100 degrees, I'll put in 373 as my temperature and put in the equilibrium constant at 100 degrees Celsius, which was 115.7, and that comes out negative 14,733 joules. So now that I have my 3 delta G values, I can calculate the Y values that I'm going to plot against the reciprocal temperatures. In the first case, it's going to be negative 7,493 joules divided by 293. For the second point, it's going to be negative 11,175 joules divided by 333. For the third point, it's going to be negative 14,733 joules divided by 373. Those are my 3 Y values. And my 3 X values will be the reciprocal of 293, the reciprocal of 333, the reciprocal of 373. So if you're going to do this on Excel, you can either make your X values in a horizontal row. So I've taken the reciprocals of the 3 temperatures, the reciprocal of 293, 333, and 373, and Excel has calculated those values. And then I've taken my delta G values divided by their corresponding temperatures and gotten my 3 delta G over T values. You can do it in rows. You can do it in columns if you wish. Just the X column would go first, X values first, the Y values second. And if you select those points and actually have Excel make a graph for you, the graph will plot the 3 points. And if you say, show me the equation of the line, it'll give you the equation of the line that best fits through those 3 points. And all you have to do is look at the slope because that's delta H naught. And in this case, that equals 18,981, but because our data was good to 3 significant figures, if you notice each of our delta G naught values and each of our temperatures were 3 significant figure values, I would round my answer to 3 significant figures, so that rounds to 19,000 joules. There's my value for delta H. It's an endothermic process. If you look at what the intercept is, because it says negative delta S, you just change the sign of whatever the intercept is, and that's going to be your delta S value. So changing the sign of negative 90.417 gives me to three significant figures positive 90.4 joules per Kelvin as my value for delta S naught, which makes sense. When a solid dissolves in water, that creates more disorder, and so we would expect the delta S in this case to be a positive number.